We just saw an example where we could have multiple recursive calls inside the body of a function. Perfectly fine. I want to show you a different example now in which we could have multiple base cases inside of a problem. And for this, I'm going to use another classic old problem called Fibonacci numbers. And here's the story behind Fibonacci. Leonardo of Pisa, also known as Fibonacci, posed the following challenge. He said, imagine I put a newborn pair of rabbits, one female, one male, in a pen or an enclosure. And I'm going to assume that rabbits mate at age 1 month, and that rabbits have a 1-month gestation period. That is, they produce a new pair. The female produces a new pair at the end of a month. He's also going to assume that rabbits never die, and that the female always produces one new pair, one male and one female, every month from its 2nd month on. And Fibonacci wanted to know how many female rabbits are there at the end of 1 year. So let's do a little sort of simulation of this, and then we'll figure out how to actually solve it. So we start off with a pair of immature rabbits, a male and a female, the 1st month. At the end of 1 month, they've matured. They can therefore mate, and at the end of the next month, they're still around, but they've produced offspring, another male and a female. At the end of the next month, the original pair have produced another pair of offspring, and the first pair of offspring have matured. And that means at the end of the next month, both sets of mature rabbits now produce offspring, and another one is matured. And that keeps happening as we start generating more rabbits and more rabbits and more rabbits until we're overrun with rabbits. Question is, could I model this to deduce how many female rabbits are there at the end of a year, 2 years, 5 years, and when will Australia completely get overwhelmed with rabbits, just to take an example of a place with too many rabbits. So, what does this say? I've got a little sequence here. In fact, they're known as the Fibonacci numbers, in which I have the following property. At the end of 1 month, I've got one female. At the end of the 2nd month, I've also got one female, who's now pregnant. At the end of the 3rd month, I got 2 females, one pregnant, one not. And in general, at n months, I've got however many females there were at the previous time, and I've also got however many females there were 2 months ago. Why? Because every female alive at month n-2 will have produced one new female at time in month n, and those can be added to the number that were alive in month n-1 to get the total that were alive in month n. So there's basically the definition of Fibonacci numbers. And how do I capture that in code? Well, here I've got 2 base cases. I've got how many females at time 0, how many females at time 1. And my recursive case, notice, involves 2 invocations of that function, one for n-1 and one for n-2. And if I want to turn that into code, there it is. I've got 2 base cases. I'm doing it in one test, but I'm saying if x is either equal to 0 or x is equal to 1, return 1. Otherwise, return fib of x-1 plus fib of x-2. And if I were to run that, I can see that I can actually compute Fibonacci. Given fib, I can check that my base cases work. Fib of 0 gives me 1. Fib of 1 gives me 1. And just to do a couple of trials, fib of 2 should give me the sum of those, and fib of 3 should give me the sum of those, and fib of 4 should give me the sum of those. And you can see, in fact, it is doing what I expected it would do. Here's a case where I've got 2 base cases. And in fact, I kind of know I need it because my return here in the general case needs 2 different invocations of that function. And I need 2 base cases to make sure that I can settle that out.